In Chapter 5, we're going to be looking at the shape of simple molecules as well as the shape of some polyatomic ions. And this is important for chemists to know because if we know the shape of a molecule, we can predict some of its chemical and physical properties. And that's an important part of the scientific process. So, an important part of determining the molecular shape is drawing the Lewis dot structure. So here are some examples of two different compounds, carbon dioxide and methane. Here is the molecular formula for carbon dioxide, CO2. The Lewis dot structure we can see below it, and there are two double bonds around that carbon central atom. And we see from this graphic that the Lewis dot structure accurately represents the actual molecular geometry of carbon dioxide. The Lewis dot structure is linear, and the molecule of carbon dioxide is linear as well. Let's take a look at methane. Its chemical formula is CH4, and its Lewis dot structure has a central atom of carbon and 4 hydrogens bonded to it with a single bond. If we look at the Lewis dot structure, we would think that the bond angles are 90 degrees. And that's because our Lewis dot structure is in two dimensions. That's not actually the case. The bond angles between the carbon-hydrogen bonds are actually 109.5. So, what's going on here? First, let's go ahead and define bond angle. A bond angle is defined as an angle formed by two bonds that are connected to the same atom. So our central atom is always going to be the vertex of our bond angles. And as we just saw, the bond angles are not always predictable from the Lewis dot structures. So we're going to look at how we can use Lewis dot structures to accurately predict the bond angles as well as the molecular geometry. So this is where valence shell electron pair repulsion theory, affectionately known as Vsper, comes in. This is a model that predicts the arrangement of valence electron pairs around a central atom. So valence electron pairs can either be lone pairs or they can be bonding pairs. And once we know how many electron pairs are around a central atom, we can predict its geometry, because electron pairs are going to arrange themselves around a central atom to minimize repulsion. Electrons have negative charges, and negative charges repel each other. So electron pairs want to be as far apart from one another as possible. And we can use geometry to predict how those electron pairs are going to orient themselves to be as far apart as possible. We want to remember that an atom has 3 dimensions to work with. So let's go over some vocabulary words. First, electron pair geometry. This is the 3-dimensional arrangement, that's what we're going to be focusing on, 3-dimensional arrangement of electron pairs around a central atom. So that includes bonding electrons and it includes lone pairs. The molecular geometry, however, is just focused on how the outer atoms are attached to the central atom. So molecular geometry is determined by electron pair geometry, and we'll see that in a little bit. But these can be the same, and they can be different. So it's important that you understand the difference. Electron pair geometry is just where the electron pairs are around the central atom, and molecular geometry is how the outer atoms are attached. Okay, now think about that, okay? All right, now, your textbook has this definition of steric number, which is a very useful tool to use in the Vsper theory. So let's look at this definition. A steric number is equal to the number of atoms bonded to the central atom plus the number of lone pairs on the central atom. So before we can use the Vsper theory, we've got to draw a Lewis dot structure. And then once we have a Lewis dot structure, we can figure out what the steric number is. So let's look at some examples. These molecules, some of them are more complicated than you'll have to deal with, but they're good for an example, I think. So let's look at the steric number of this nitrogen. We're looking at that nitrogen as our central atom. Its steric number is the number of atoms that are bonded to it plus the number of lone pairs. So there are 1, 2, 3 atoms bonded to it plus a lone pair. This would have a steric number of 4. We look at this carbon, the steric number is going to be 2 because it has 2 atoms bonded to it and no lone pairs. Here in this molecule, our phosphorus has 3 atoms bonded to it and 1 lone pair, so it has a steric number of 4. This carbon here has 1, 2, 3 atoms bonded to it and no lone pairs, so this carbon would have a steric number of 3. If we look at this oxygen, it has 2 atoms bonded to it and 2 lone pairs, so it would have a steric number of 4. And then down here, carbon dioxide has 2 oxygens bonded to it and no lone pairs on that central atom, so it would have a steric number of 2. This carbon here has 2 atoms bonded to it and no lone pairs, so it has a steric number of 2. Your examples will have a clear central atom, but we can see how important it is to identify what the central atom is, because that determines the steric number, and it also is how we determine the molecular geometry based on how atoms and lone pairs are arranged around that central atom.